We are on FRQ Topic 2, Graphical Analysis. These problems are going to look familiar to you, even though it's been a while since we have done these types of problems. This topic shows up a lot on the BC exam and on the AB exam, on both of them. Very few years have there not been any graphical analysis question. These are going to be your no calculator question. To begin with, I'd like to review our Fundamental Theorem of Calculus. We're very familiar with the first part of the Fundamental Theorem of Calculus, which says if you have some value of f minus another value of f, that is the integral from a to b of f prime dx. Okay? We can switch those two sides, of course, and we often see it that way as well. We use this every time we evaluate a definite integral. We use the Fundamental Theorem of Calculus. So that's the first part of Fundamental Theorem of Calculus. This is the one we recognize rather easily. The second part, though, is when we're taking the derivative of an integral. The derivative of an integral. And I'm going to put boundaries on here, so it's going to be a definite integral. These boundaries can be anything. Specifically, since we're taking the derivative with respect to x, these are potentially going to have x values in it, or a function of x in here. So since this is going to be a function of x, I'm going to write my function over here, my integrand, as a function of t, because I don't want to have x's on the boundaries and x's in my integrand. So I'm going to write this in the most broad sense first. Let's say that this is g of x, some function of x, and this is h of x, another function of x. When we're taking the derivative of this integral, this part of the Fundamental Theorem of Calculus says, and we explained it back when we were first going over this, you start at the top boundary and you take the derivative. It's a bit of a chain rule going on here, so you need the derivative of that first. Then you replace every t in your function with that function of x. So this is going to be times f of h of x minus, now we go to the bottom boundary and do the same thing. Take the derivative and then multiply by the function evaluated at that function of g. Okay? Oh, no dx. Nope, I have it. Okay, so that is just our answer there. So, for example, if we had, let's say, x to 3x squared of natural log of t squared dt. This would be, we start at the top, take the derivative, and then multiply by, and we're going to replace t with 3x squared. If we replace t with 3x squared, that's going to be 9x to the fourth. Minus, the derivative of x is just a 1, and then we're going to replace t with x. And that will be our answer. That's the derivative of that integral. You can only do this when you're taking the derivative of an integral. Oftentimes, we're taking the derivative and the bottom boundary will be some constant, any constant, and the top boundary will just be an x. When that happens, the derivative of x is just a 1, replace t with x, minus the derivative of 3 is 0, so that second part of this is just 0. So the derivative of this is just f of x. We see that a lot, particularly in these FRQs. Now let's go and take a look at a problem. So I'm going to start with the problem from 2018. This was number 3, no calculator. And by the way, in 2018, the global average on this problem The global point average, out of the 9 possible points, the global average was a 5.3. It's pretty high. It's pretty high for one of these problems. Well, for any FRQ problem, that's pretty high. The KHS average was a 6.0, so a little bit higher. All right, let's take a look at this problem. The graph of a continuous function g, the derivative of f, is shown. The function g is piecewise linear for -5 to 3, and then they give us an equation for g for 3 to 6. I'm trying to sharpen this up a little bit. Okay. All right. So g is the derivative of f. G is the derivative of f. So g equals f prime. They're giving us that in this problem. In fact, I'm going to write that, well, I will write that when I need it. Well, and I'm going to need it right away because they're asking me a question about f, right? So g is f prime. I don't really have to write it because they gave it to me, but it'll help me keep things straight. So this graph of g is also the graph of f prime. I'll remember that. So in this first part, they give me a value of f, and they want me to find another value of f. First fundamental theorem. When they give me a value and ask me to find another value, and I have information about the derivative, first fundamental theorem. So I'm going to set up the first fundamental theorem. I always start with my larger x value, which is 1 in this case, minus f of -5, and that will equal the integral -5 to 1. Remember, your upper boundary has to be the first x value listed, of f prime. So this is the graph of f prime. So when I'm finding the integral of f prime, I'm looking at areas. So f of 1 was given to me. And over here, I'm going to use my areas from -5 to 1. -5 to 1. So I'm seeing this square area. There are 9 square units in there, and it's below the x-axis. So I'm making that a -9. This next piece is also below the x-axis, so I'm going to make it negative. It's a triangle, so that equation of an area of a triangle is 1/2 base times height. So 1/2 1 times 3. From -1 to 0, there's no area, and so I move on to 0 to 1, which is another triangle. It's above the x-axis, so this is going to be positive 1/2 the base times the height, 1 times 2. So then f of -5, solving this for f of -5, I would bring it to the right where it would be positive, so I'm moving all of this to the left, and I'm just going to safe stop this. So I'm moving this -9 to the left. It'll make it positive. This next one will be positive. The next one will be negative. And I'll just safe stop there. Part B. Oh, this was worth 2 points. 1 point for the integral, 1 point for your answer. Part B. Evaluate this integral. Evaluate the integral from 1 to 6 of g of x. Well, this is the graph of g of x. So the integral here is just going to be, it's going to involve areas, right? The areas, I'm going to be able to count the areas for a lot of this, but over on this section, I'm not going to be able to count it. I'm going to need to use an antiderivative, and I'm going to need to put in that function for that part of g. So I'm going to begin by something I have to do, which is I have to split this up into its 2 parts. From 1 to 3, from 1 to 3. And then I'm going to add from 3 to 6. From 1 to 3, I can just count my squares. From 1 to 3, that's just 4 square units. From 3 to 6, I'm going to need to use the function here. So 2 times x minus 4 squared dx. And so this one I'm going to need to evaluate by hand because we don't have a calculator. I'm going to do a little u sub here, but I'm going to do it in my head because when u is x minus 4, du is just dx. So I'm treating this like a u. I'm treating it like a u. So this will be the 2 that's out front times the antiderivative of u squared is u cubed times 1/3. Except instead of the x, I'm putting a 4. Goodness. Okay, let me write that again. 4 plus 2 times u cubed times 1/3. And we are evaluating that from 3 to 6. So we have 4 plus, this is 2/3, times, if I put 6 in for x, I'm going to get 2 cubed, minus 2/3. If I put 3 in for x, I'm going to get a negative 1 cubed, and that would be a safe stop spot. So I will leave it like that. This was worth 3 points. 1 point for splitting the integral into its 2 parts at x equals 3, it says. 1 point for the antiderivative of 2 times x minus 4 squared, and then 1 point for our answer. So this antiderivative here was worth a point. Splitting the integral was worth a point, and then of course the answer was worth a point. Part C. For negative 5 to 6, on what open intervals, if any, is the graph of f both increasing and concave up? Well, f in general, f is increasing when f prime is positive. F is concave up when f double prime is positive, right? So this is the first time that we, in this problem, that we have dealt with f double prime. So I need to say what that is in this problem. I know what f prime is, and I've said what f prime is, but I have not said what f double prime is. And f double prime is the slope. It doesn't imply this. I'm just saying f double prime is the slope of f prime. Or you can say the slope of g. Either one, because f prime equals g. So, f is increasing and concave up on, all right, so I want f prime to be positive and f double prime to be positive. So I want this graph to be positive, and I want the slope of this graph to be positive. Well, the graph is positive above the x-axis, and I'm going to look for the positive slopes. So we have a positive slope from 0 to 1, and then we have a positive slope from 4 to 6. So 0 to 1 and 4 to 6. They told me to use open intervals, which we always do for concavity. So I'm going to make sure I do not close my intervals here. This was worth 2 points. 1 point for the intervals, 1 point for the reason. Part D. Find the x-coordinate of each point of inflection of the graph of f. Well, I'm going to begin with my reason. F has a point of inflection when f double prime changes signs. I've already said what f double prime is, so I don't need to say it again. I'm just going to go and look for where f double prime changes signs. And f double prime changes signs. Okay, here are my interesting points. Right here, does the slope of change signs here? Well, the slope goes from 0 to positive. Is that a sign change? The answer is no, that's not a sign change. A sign change is positive to negative or negative to positive. Not a sign change. 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 Here we have a sign change because we're going from a negative slope to a positive slope. So only at x equals 4. So f has a point of inflection only when x equals 4. This was worth 2 points. 1 point for the answer, 1 point for the reason. Okay, next up I would like to take a look at number 3. I'm sorry, not number 3. Well, it is number 3 in this packet, but I know these packets are going to change over time. So this is the problem from 2016. The problem from 2016. It was number 3, no calculator. The figure shows the graph of the piecewise linear function f, -4 to 12, and the function g is defined by this. As soon as I see that, I know the type of question that they're going to ask me everything about g. And I'm going to need to write what g prime is, and I'm going to need to write what g double prime is. I know when I see that that's coming. Part A, does g have a relative min, relative max, or neither when x equals 10? Well, g, in general, ignoring the entire problem, any function has a relative min or max when g prime changes signs. So g has a relative max or a relative min when g prime changes signs. Okay, so I need to say what g prime is. G prime, I'm taking the derivative of this integral. The derivative of this integral, so this is that second part of the fundamental theorem. This is just going to be f of x. So this graph of f is also the graph of g prime. So at x is 10, do we have a sign change of g prime, which is this graph? Is there a sign change in the graph? No. The slope changes signs, but we go from below the x-axis to below the x-axis. There's no sign change in the graph of this function. So at x equals 10, g has neither a relative min nor a relative max, since g prime does not change signs. There. This was worth just 1 point for the, oh, I'm sorry, I'm on the wrong problem here. Hang on, let me see. Okay, it was worth 1 point for the answer with the justification. That's on our next problem over here. Okay. Part B, does the graph of g have a point of inflection at x equals 4? Well, point of inflection. Point of inflection is when G double prime changes signs. So I need to say what G double prime is. G double prime is the slope of G prime, which is also f of x, because up here we said G prime is f of x. So G double prime is the slope. So we want to go up and look at x equals 4 and ask ourselves, is there a slope change, a change of sign in the slope? So at x equals 4, we're up here, and yes, the slope did change signs there. So at x equals 4, G has a point of inflection since G double prime changes signs there. This was worth 1 point. Answer with justification. Part C. We must be getting some bigger pointed parts soon. Find the absolute minimum value and the absolute maximum value of G on this interval. When I see absolute min or max, I think closed interval test. So I'm making a closed interval test. My independent variable is x. I'm finding the absolute min and max of G. So that goes over here. Whatever you're finding the min and max of, that goes over here. We start with our boundaries. And then we also want to put on here any value of x that causes a sign change in G prime, right? So G prime equals 0 and changes signs at, all right, up here, this is the graph of G prime. Here G prime is 0 and it changes signs. So at x equals -2, here G prime is 0, but G prime does not change signs here. Here G prime is 0 and we have a sign change. So I'm putting, oh, well, okay, I'll put -2 and 6 over here. And here G prime is 0, but we don't have a sign change. So I don't need to put 2 on there, and I don't need to put 10 on there. All right. Okay, so I need to find out these values of G. So how do we find out the values of G? Well, here we have an equation for G. So I'm going to use that equation and put a variety of values in for x. So G of -4 is the integral from 2 to -4 of f of t. All I did was I replaced x with -4. So this is, since my lower boundary is on top, I need to switch that and put it on the bottom, which I definitely need to do if I'm dealing with a graph, if I'm getting values from a graph. So this is the negative of the area under f of t, which is right here. That's f. So from -4 to 2, -4 to 2. I'm looking at that. Well, from -4 to 0, these two areas will cancel each other out, because one will be, we're going to have a negative of this area and a positive of this area. So they'll cancel each other out. Then I'm only left with this piece, and it's positive. So positive 1/2 base times height, 1/2 2 times 4. So 1/2 2 times 4. I could leave it like that, but since I'm going to be comparing values, I'm going to simplify this. This will be a -4. So when x is -4, G is -4. Now we're going to go on to, my next in line is 12, so I'm going to go to 12 next. 2 to 12, f of t dt. So all I'm doing is replacing the x with a 12 in the formula for G. So this time I don't need to switch the boundaries, and so I don't need a negative or anything like that. So I'm going to go from 2 to 12, from 2 to 12. Well, this area and this area cancel each other out. So from 2 to 12, I only need to consider this area here. It's below the x-axis, so I make it negative. 1/2 base times height, 1/2 2 times 4. So negative 1/2 2 times 4, which again is negative 4. So when x is 12, g is negative 4 still. G of 6 will be the integral from 2 to 6. Well, from 2 to 6, I'm completely above the x-axis, and this is another triangle, 1/2 base times height, 1/2 4 times 4, which is 8. G of negative 2 will be the integral from 2 to negative 2. My smaller boundary is on top, so I'm going to flip that, make it a negative, negative 2 to 2. So from I'm going to have a negative of what I'm about to go and evaluate. So negative 2 to 2, negative 2 to 2 is here. It's this triangle. So 1/2 base times height, 1/2 4 times 4 again. So this will be a negative 8. Negative 8. So we were asked to find the absolute minimum value and the absolute maximum value of g. So the absolute maximum value is 8. The absolute minimum value is negative 8. So I'm going to write that down. The absolute max value of g is 8. The absolute minimum value of g is negative 8. My justification is the closed interval test that everybody can see here. That all of this is my justification. Okay? This was worth 4 points. Try to squeeze it in right here. This is worth 4 points. 1 point for considers x equals negative 2 and x equals 6. 1 point for considers x equals negative 4 and x equals 12. And then 2 points for your answers with justification. So big points on an absolute min-max problem. All right, for part D, it says on this interval, find all the intervals for which g is negative. G is negative. Up here we have a little table for g, and we do have a lot of negative values. Let's see if we can reason this out. In fact, I might just come over here and sketch me a little graph and see what's going on here from negative 4 to 12. I know at negative 4 I'm negative. In fact, I'm negative 4. Negative 4, negative 4. And then at negative 2, I go down even lower. I'm down here at negative 8 when I'm at negative 2. Now, when I'm at 0, we didn't find x equals 0, but when I'm at 0, if I have gone, I'm increasing, g is increasing, because g prime is positive here, and it's increasing at the same rate that it was going before. So it makes sense to me that at 0 I'll be back to negative 4. Okay? When x is 2, we are at 0. When x is 2, the integral would be 0, right? So we are at 0 there, which again makes sense to me because it's the same. We're always moving by 2's, right? We're always moving by 2's. So when x is 4, we should be 2 higher. I'm sorry, x is moving by 2's. So when x is 4, we should be 4 higher. So we'll be up here at positive 4 when x is 4. When x is 6, G prime is still positive, so we're going up even higher. That's how we got that 8 there. For when x is 6, we're at 8. When x is 8, we should, now we're going down, we should be back to positive 4. When x is 10, we're at 0. And when x is 12, we have that on here, we're at negative 4. So it makes sense to me that G is going to be looking something like this. Something like that. Okay? So we are negative G of x is less than or equal to 0 on negative 4 to 2 and 10 to 12. I'm including the boundaries because it said equal to 0 here too. Alrighty. This was worth 2 points just for those intervals. We did not have to describe why, and I'm glad we didn't have to justify why, because that would be hard to explain why. Now, there may have been another way to do this, but that's the way I saw to do it. Okay? So that was that problem. A little bit tricky at the ending. I don't have the global average on that one. The next one I'd like to do with you is the problem from 2013. So grab your problem from 2013. And on this problem, we see it looks a little bit different. They did give us the graph of f prime. The figure shows the graph of f prime from 0 to 8. F prime has horizontal tangents at x equals 1, x equals 3, and x equals 5. So they're telling us that those are indeed, they look like horizontal tangents, and they are horizontal tangents. The areas of the regions are given, and then they give us a value of f. Here I know they've given us a value of f, and they're giving us information about f prime, so we will be able to find any other value of f that we are asked to find using the fundamental theorem. Find all the values of x in the open interval for which the function f has a local min, and we have to justify. Well, f has a local min when f prime goes from negative to positive. From negative to positive, and here's the graph of f prime. So where does f prime go negative to positive? F prime goes negative to positive right here. So that is at x equals 6. So f has a local min when x equals 6. This was worth 1 point for the answer with the justification. Part B. Determine the absolute minimum value of f. On the closed interval 0 to 8, we have to justify closed interval test. The independent variable is x. We're finding the absolute minimum value of f. I begin with my boundaries. And then I also put any values of x that could be a relative min. A relative min. Well, in part A, we found the value of x where f had a relative min. So I know I'm going to be putting 6 down here. Now I need to tell AP why. And so I'm going to say f has a relative min when x equals 6. So I'm putting 6 down. Do I need to put down x equals 1? No, I don't, because that's not even a candidate. It's not a candidate for an absolute min. Would it hurt to put x equals 1? No, it's not going to hurt me, but it's not useful for me either. It's also not useful for me to put x equals 4, because that would be a relative max for f. And I don't need to put a relative max value of x if I'm looking for an absolute min. So the only thing I have to put on here is 6. Now, do I have to state this again? Probably not, since we stated it up here. We probably don't need to say this, but just in case, I'm going to put it down. If it's worth a point, I'm going to put it down. All right, so now we need to find these values. They gave us f of 8 was 4. I need to find f of 0 and f of 6, and I'm going to use the fundamental theorem to get there. So f of 8 minus f of 0 is the integral 0 to 8 of f prime, which means f of 0 would be my f of 8 minus the integral, And the integral from 0 to 8, it's the whole thing, is going to be positive 2 plus 6 minus 3 plus 7. So hopefully, since we have to compare, I'm going to work this out. This is 8 plus 7 is 15, minus 3 is 12. 4 minus 12 is a negative 8. So I'm hoping I did that right. Now let's go and find f of 6. Now, to find f of 6, I could use the 0 or I could use the 8 in my fundamental theorem. It doesn't matter which one. I think I'm going to use the 0 since I just found that value. 0 to 6 of f prime. So this time we're solving for f of 6. So this will be my f of 0 when I take it to the other side, so negative 8 plus my integral from 0 to 6. The integral from 0 to 6, here's x equals 6, so I'm going to need 2 plus 6 minus 3. 2 plus 6 minus 3. So let's see, that's going to be a negative 3. Negative 3. So the absolute minimum value of f is negative 8. My justification is that closed interval test. Or you can, if you really want to, you can say by closed interval test, but it's unnecessary. This was worth 3 points. 1 point for considers x equals 0 and 6. Had to consider x equals 0 and 6. 1 point for the answer. 1 point for the justification. On to part C. On what open intervals from 0 to 8 is f both concave down and increasing? Okay, well, f is increasing when f prime is positive. And we have the graph of f prime. F is concave up when f double prime, down, when f double prime is negative. I need to say f double prime, it's not implies, f double prime is the slope of f prime, because that's what I'm going to be using to figure this out. So I want f prime to be positive. This is the graph of f prime. F prime is positive above the x-axis. And I want f double prime to be negative, so I want the slope to be negative. So above the x-axis with a negative slope. 0 to 1, 3 to 4, and that's it. Everything else is positive slope. So 0 to 1 and 3 to 4. So f is both increasing and concave down on 0 to 1 and 3 to 4. open intervals for concavity. So open intervals here. This was worth 2 points. 1 point for the answer, 1 point for the justification. Okay, next step, part D. The function g is defined by, now they're throwing in a new function, function g. G is defined by this, and they give me f of 3 is -5/2. Find the slope of the line tangent to g when x is 3. Slope of the line tangent, I know, is g prime. So they're asking me to find g prime at 3. Well, first we need to find g prime at x. Need to use the chain rule here. This is a question asking, does this student know the chain rule? So, yes, we do. Start with your exponent, multiply it by your coefficient, decrease your exponent by 1, leaving your inside the same. Then you multiply by the derivative of the inside. That's the chain rule. Next up, we put 3 in for x. So we'll have f of 3 squared. They gave us f of 3. And then we need f prime of 3. F prime of 3 is, here's the graph of f prime. So f prime of 3 is just 4. So this is just 4. And that would be a safe stop spot. So I'm going to safe stop. This was worth 3 points. 2 points for finding g prime of x using the chain rule. There's a lot for a chain rule. And then 1 point for our answer. So that's how that was scored. Okay, there's one more thing I want to tell you before I go, and that is this. When you are doing the problem from 2019, it's problem 2019. The global average for this question was 4.7. The KHS average was 5.3. Okay. Keep in mind that about 45% of KHS students get an A. Get a 5 on the exam. Okay. Another 20%, about 22%, something like that, get a 4. So that means if you can get that KHS average, you're set, you're on target for either a 4 or a 5. Okay? So when I give you these averages, that's what I'm getting at. If you can get to these averages, you're in really good shape to be on track to get a 4 or a 5. So shoot for these averages or higher. Okay? All right. Your turn to go work some of these problems.